So mark the points that are being sampled in the following waveform. So this one is being sampled, and this one is being sampled. Only 2 points you can see on the diagram. Not anyone else, just this one or this one, because this one is being sampled and then being held for this DC voltage over here, and this one is being sampled for the DC voltage following that point. And second, mark the period that the SAR conversion takes place. Exactly just this period. Okay, that's when the conversion happens. Third, is using 50% duty cycle for the sampling voltage is a good idea, and why? So it's not a good idea because look at this. This is 50% duty cycle. So what does that mean? 50% duty cycle. So this and this, B, A equals to B. That's 50% duty cycle because this is one period. This is one period. And on time or off time for both of them are 50% of the whole of the entire period over here. This is called 50% duty cycle. But this apparently this is not. This is like 20% or so, like even less. I think 10 to 15%. I don't know. I'm just looking at the width here, and here this is the whole period, right? Just look at this. This is probably like only 10% or 15%. So that's why we don't use 50% duty cycle, because we don't have to let the output to track the input for a long time. After this one has been sampled, I mean literally, did you see this little time delay over here? You can see that, right? So you can see the time delay here. And actually for the width of this on time, as long as it's slightly longer than that time delay, for example, you just stop here, which is also fine. We just didn't do that. But if you want to do that, which it's going to work. So you definitely don't want a 50% duty cycle because it takes a lot of time. And after that point, it's just tracking the signal but not doing anything else. And until here, it's sampled, right? So actually it only samples this point. So why do you need the sample hold to track the input for that long? You want to stop it whenever it's ready, then just sample it. Yeah, and then take the time to the conversion, because this is the most time-consuming task, right? So you want to keep that rising edge or keep that time on to be short, and then just take the time to the conversion, and that's the whole period. That's the whole cycle. It's done after that. Okay. So 50% duty cycle is bad. What about this one, the second one? So there are two questions, okay? So in the following started, why do we need a clock door register as the first question? And why do we need a DAC to be connected to it to provide a VL? So the DAC to be connected to the clock door is to provide a VL, not this stack, okay? It's this stack. All right, so this one is being used to only send the correct result to the output. That's why we need this door here. It waits until the 9th clock to send the good result to the output. And why do we need a DAC to connect to the door clock? The door register is used to provide this VL so we can recover that analog input voltage, even though there will be stars, but you can compare the VOut to the VIN and to validate, we're trying to evaluate the performance of the ADC. So these two decks are doing different jobs, right? So this deck is providing a feedback signal to the comparator. And this one is to provide a, so if there's only one pin, it's going to convert that digital output into a one pin or one line signal, so you can compare with the analog input. So see this and this. All right, and that's why, you know, in the senior SAM project, we have to have a DAC to be connected to the dual register, so we can short it to what? To audio amplifier. So what's the best way to verify if the ADC system works? So we inject the music, you know, a song, to the input of the ADC. And if you only look at the digital output, they are just 1 and 0. So if you only look at this one, it's just a discrete signal, right? How do we verify it? You can tell if the sound is correct, right? You can hear that. So that's why we need a DAC and connect to audio amplifier, and then use a speaker to amplify it. So definitely the circuit here is more complicated than just one box. But the thing is, this is how we verify it. So you can tell the ADC works over here. All right. What about this one? Explain why the sample hole clock signal should be the inverse of this one. Because whenever the conversion takes place during this period, so when the set and reset of the SAR block is high, so it's not providing the 1 and 0 zeros, that initial state. So it's doing the conversion. During that time period, you don't want to sample any new data. You want to hold it. That's why here, see, when the sample and hold is low, it's holding the data there. It's not sampling new data, right? That's why during the new cycle, during the conversion cycle, you need this to be low. So it's not sampling new data. A quick question, okay? So look at this pulse here. So what's the difference of this pulse and this pulse? So see the pulses here? So what's the difference of this series of pulses compared to these pulses? What's the difference? You're bumped. What's the difference of this signal and this signal? I mean, I've recommended a few times, you guys should go back and download that LT-Spice and signal and run it. Just run it a few times. I think I brought this up at least 2 weeks ago, and you should have started already, but probably you haven't. So what's the difference between this sample and hold pulse and this? No difference, they're the same signal. Okay, just let you know. What we are looking at here is exactly here, all right? And you just need to simply invert it to create another signal. It's very convenient, just invert it, you get another one. You don't have to design a very complicated counting logic, timing logic to do it. And what about here? So the counter has for output, right? They are being shorted to these ones, Q4 to Q1, 1, 2, 3, 4. And the counter starts with 0, 0, zeros, right? All zeros. It's going to start counting like flipping this digit, 1 and 2 and 3, right? And keep going until 1, it's going to output a 1 here. Counts to what value? It's going to output a 1. If you need a 1, this 2 needs to be 1, right? For the AND gate. And all these need to be 1. Is that correct? So this need to be 1, this need to be 0, this need to be 0, this has to be 1. So what's the number here? What's the number it's going to count to? 9. So at the 9th cycle, it's going to output a 1 here. That's how to design the counter, right? So the counter with a customized number there, but not if you have a 4-bit counter, what's the maximum number it's going to count to if you don't have any control of it? Yeah, 15. So start from 0 until 1111, right? But you want to control it. So that's how you can control it. Use the combinational logic, use the logic gates. Make sense? Questions? Anything? So start the project earlier, okay? Don't wait until the last like 1 week or 2 weeks. How many weeks we have? Okay, yeah, 3, including this week. Yeah, the break, you probably want to break. Ski. If we get some snow, we're lucky. But 3 weeks. Yeah, start working on that probably today. A lot of work in there. So for inverter, 2 inverters, let me see where I'm gonna start it. All right, from here. Still keep working on the digital model design, models for digital design, and then we're going to introduce a model for ring oscillators and clock the circuits. Then we are probably done for that part of the textbook. Models. Do a quick review on that. Inverter here, and the model looks like this. That's to break it because it's a gate. All right, a quick quiz question here. What are these caps? Oh yeah, CP, but it is 3/2 of Cox P, right? Is it? On the top, this has a Miller effect or not? No. 1/2. What about this one? It has a Miller effect. So it becomes 1/2 of Cox P. That's why overall, there's 3/2 of Cox P. For this one, this is 3/2 is coxN. And this is Rn, this is RP, Rn, the channel resistance. And this is, because it's a Miller effect, right? So this one got cox P and cox P for the output as well. So this is just cox P, 1 times of cox P, and this is 1 times cox N. Right? So here's an example. Estimate the intrinsic propagation delay of the following inverter. It's very simple. Because all the parameters are given. So this is on the page 320 of the textbook. So the parameters are like the following. NMOS is 10 to 1. So the actual dimension is 0.5 micrometer over 50 nanometer. And Rn is 3.4K. Cox N is 0.625 femtofarads. For PMOS is 20 over 1, which is 1 micron over 50 nano. And RP is also 3.4K, and Cox P is 1.25 picofarads. The time delay will be propagation time delay will be TPLH and TPHL. So only look at the output. Because output is the point being driven up and down. So you are only looking at here. So what is TPLH? Sorry. 0.7 R watt, C watt. LH. Yeah, low to high, right? It's being pulled to the VDD. C. Yeah, C total. It's very simple, right? Just Cox P plus Cox N. And that's it. For TPHL, 0.7 times Rn times C total as well. So the C total are the same. They are simply just Cox P plus Cox N, right? And same here as well, because the RP and Rn are the same in this example. It's very simple for the calculation for this type of problems. Okay. And so what if there's a capacitive load being connected to the inverter, for example? So this inverter is driving a 50 femtofarad. Okay. Oh, this shouldn't be should be femto, not pico. The pico is too big. Sorry, femto, not pico. So in that case, if this one is being shorted, the output is shorted to a 50 femtofarad cap. If you compare this capacitive load with Cox P and Cox N. This is only like 0.625 femto. This is only like 1.25 femto. And the load here is huge. So if you draw the capacitive load to the model here, it's just simply getting another cap in parallel with all the other caps. So you can definitely ignore all these smaller ones, right? This one, this one. So C total becomes this. Okay, whenever you see a big cap in the load, just directly replace it. Replace the original cap with the load because this is significantly larger than all the other caps. And now let's look at the ring oscillator. So you have laid it out somewhere in the lab, but we haven't covered the theory behind it. A quick question here: if I got 4 of them, can I oscillate it? The answer is no. And you are thinking like, there's no input. Why can I get an oscillated output from this circuit just by feeding it back to the input? Because every stage has a time delay. And for example, the voltage here, it cannot, for example, the switching point of the inverter is 2.5 volts, right? You can only hold that inverter stable at 2.5 volts because if you look at the input and output curve, remember that curve? Here's in, right? Here's out. Which pin or which point makes the inverter stable? The input and output stays at that voltage but not changing to anywhere. Here, right? But it has to be exactly 2.5. Usually it won't happen. And a little noise is going to trigger it. It's a little higher than 2.5 is going to trigger the change. All right. So in that case, for example, the voltage here at some point, I know there's no input, but at some point the input here start rising. So what's going to happen to this point? So start falling, right? And here it will rise and fall and rise. So it's not going to change this any, I mean, how do we explain that? So, I mean, we have to look at the one has the odd number of oscillators. So this output here is the same. It's the same pin, same wire. So this still has the same rising edge. It's not changing it. It's not toggling this input. But for this one, so definitely you know that it's going to toggle it. Right? It's going to toggle it. Oh, sorry. So it's hard to imagine, but think about it. How it's happening? What's happening here? So what's happening here? Yeah, it's going to flip it, right? So and that takes time. So it's like this one, for example, this one start rising, right, at some point, and after a while, it's being flipped back to ground. Why you have this here? Time delay of each point. Why time delay from each point? Because of this propagation delay by the caps and resistors, right? So that's how that works. I mean, if you're looking at the inverter's time domain analysis, it's going to oscillate like that. And why you can see this oscillates in the time domain? It's because of time delay, yes. Just actually like there's a change. If there's no, it's not being expanded or stretched in the time domain, it's only oscillate in one place, then it's gonna like just one point oscillating back and forth, right? But if you stretch it in time domain, you'll see the oscillation like this because of the time delays. And this is only one period. So what is this time delay from here to here? That's TP what? HL. Let's label as 1. So what is this? LH2. What is this? HL3. If you add them together, and it's going to be this time delay over here. And this is the half of the period of the oscillation. Is that correct? So on the time on, we're not considering the time off yet, right? Because the period here has time on, time off. So what about the other side? After this is being put down to the ground, and then you got another cycle, right? So this is this, 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 and then it's gonna pull it up to VD again. So what's the time delay here? TP. And add them together, and that's another half of the period. So you got both time on, time off for the period of the ring oscillator, and so 1 over T will be F, right? So we can calculate for the frequency of the oscillator. And so the question here, like if you need a faster oscillation, do we want more inverters or less inverters in there? Less. Why? Yeah, less these things, right? So less of these things, which means you got a smaller T. So smaller T will give you a higher F. So frequency will be higher. So the fastest oscillator we can make consists of how many inverters? No, it's not going to oscillate, right? No, one is not going to oscillate, just flip the signal. No, it's still not. Is it? Yeah. Good question, actually. I mean, will this work? Theoretically, yes, right? Yeah. Yeah, possible. Okay. So what's the equation to calculate for the oscillation here? So I have a half, I have to add them together, right? Is that really a half? Depend on the size of the PMOS animals, right? The RNRPs. But definitely, if you add them together, you're getting 1T. No doubt over there, right? So you want to add all of them together, and it becomes n times, so n is the number of inverters we have in the circuit, not n plus, n times TP HL plus TP LH. Is that correct? So this is 1 times of TPLH plus TPHL. You have 1, 2, 3, 4, 5, right? Times 5. And 1 over it, which becomes the frequency of the oscillation. Okay? Any questions here? So now let's look at what are these capacitance involved in these TPHL and LH. So that point is a joint here. So I'm not shorting them, but just trying to show you that this is the same point in the model. So this is Cox P, this is Cox N. This is 3/2 of Cox P. So what is TPLH? R what? Rn, right? LH. Oh, RP. So what's the C total here? So this is 5/2 of Cox P and 5/2 of Cox N. Right? TPHL. So a quick example, estimate the frequency of the oscillation of the 11-stage ring oscillator. So F TPLH is C total is and if you plug in all the numbers in there, we're actually getting F oscillation equals to 1 over 11 times 22 picoseconds. See how fast it is. 4 gigahertz. So a lot of times, if you want to provide a slower oscillation or clock, you have to add a lot of stages of inverters in there. So 11 stages is just giving you this. So what are the other ways can make it slower? Where? Oh, at one of the stages. That may work. Let's see. Yeah, that is gonna work, right? Just add it to anywhere. But will that be? I mean, it's gonna be tricky because you're gonna have different TPLH and TPHLs, right? The delay here will be different from the other ones. Every single one of them, yes. And caps are taking a lot of space on the chip, right? Yeah, that works. And also adding more stages, adding some caps to it, and or increase the size of the transistors inside the inverters, because you can see the caps, right? So this is calculated by the clocks equals to what? Clocks prime times A, right? So increase the area, which is the width and length at the same time of the caps. So you can increase the clocks of clocks and clocks P as well at the same time. All right. You cannot add resistors into the transistor, right? Have to make sure it's going to flow through that, because it's only so the resistor only works whenever it runs through it. You put a resistor here, then it's going to be in parallel with this one. It's actually reducing the resistance. Oh, in here? Yeah, in here. Right? Just put it in series over here. Yeah. That may work as well. Because every time it has to run through this resistor, either up and down, it has to, that's the critical path, has to run through it, right? All right. Dynamic power dissipation of the inverter of the digital circuit. It's just one equation to show you guys. So inverter is driving a cap. Digital input. So what's the power consumption of this type of circuit? It's not just the inverters. This is just a digital model of everything. It's just going on and off and driving a cap. So it's injecting and pulling current with different cycles. So you can calculate the I average current goes through this cap is Q total over T. The Q over T is the I, right? Just in average. It's not linear, but in average, the total Q over total time. So Q equals to VDD times C total. So whatever capacitance, effective capacitance at this node will be the C total and over T. So that's the average current running in the circuit. And power average equals to I average times VDD. Which is giving you, just plugging this one to here, the VDD squared times C total times 1 over T is literally just the F. So F is the frequency you run these pulses. So for digital systems, not just the inverter, this is just a model. For every digital system in your smartphone, your computer, everywhere, these are the factors to determine the power consumption. So whenever the fabless companies are making faster and faster CPUs, they want to run from like 1 gigahertz to 4 gigahertz, and you know that it's going to consume more power, right? It's oscillating faster. If you have a large area in a circuit, you have a lot of parasitic caps. This is going to increase the power consumption as well. What about this one? Yeah, so 40 years ago, like the chips we fabricated 2 years ago, we used the C5. To, also, you guys are using C5, right? It's a 500 nanometer technology. And what's the threshold voltage of it? No, threshold voltage for the NMOS turn, like somewhere around 0.6 to 0.8 volts, right? So definitely you don't want to operate it at 1 volt. So that's why the typical voltage of that huge is considered as a very big, very old technology. We're using 5 as VDD. And that's another, because it's consuming a lot of power, because you have to charge and discharge the cap in the 5 volts range. Just consume a lot of power here. Just want to reduce it to smaller technologies, which does not require 5 volts VDD. So you can still use like 2 volts, 1.8 volts to turn it on and off. If you can do that, why do you still want to use 5 volts, right? That's why right now the current technologies are always running at 1 or lower than 1 volt as a VDD for all the circuits in your phone, smartphone, or laptop. And 5 volts is a C5, and also for Arduinos, right? Remember, if you have played with Arduinos, the Arduino chips, the microcontrollers on the Arduino board, these are fabricated in 350 nanometer technology. Usually, it's very close to this. So the Arduino boards, you toggling the LEDs or making displays on the LCDs, control motors, these kind of things. These are actually very old technologies. That's why you can buy it under $2 for each chip. But the Arduino board is still like $10 to $12 for the board itself, because the cost involved in other components on the board, also the PCB fabrication. But for the chip itself, the CPU itself, is only $2 or less. And the one we are doing for our senior son project is a TSMC under 80 nanometer technology. So the largest volts you can use to the green of the NMOS I mean, sometimes there will be a little difference from the maximum voltage rating for the gate and drain, but for the 180, I think it's 2.2 volts, right? Cannot be more than that. Otherwise, it's going to blow up the transistor. So 2.2 volts will be the highest, but typically we use 1.8 volts for VDD. And it's 180 is not even like the 5 nanometer being used in your phone. It'll be a totally different story. Right? Okay. That's why we have the motivation to use lower voltages, because it's lowering the power consumption, so your battery in the phone can last for a longer time. But anyway, it's oscillating faster, so it's still consuming a lot of power. It's better to reduce one of the factors, at least if we can do it, right? Why not? What is the other problem whenever you oscillate your chip faster and which consumes more power? I mean, yes, it's saving the battery or killing the battery faster. Depends on you have a high or low frequency. I mean, what's the other consequence of running your circuit at a very high frequency? Errors? Yes, but usually when they design it, they will control it with a reasonable frequency, right? Make sure everything will be set up before you trigger it. Yes, there will be more errors because the design process will be more complicated, right? Heat. Right? It's going to generate a lot of heat, so your chip becomes hot a lot faster if you run it slower compared to that, okay? Yeah, that's everything about digital design. And then we have some other materials for clocked circuits. So there will be a totally different design of flip-flop using transmission gate. Just to let you know, the D flip-flop we used in our design is not the only option you can use. A level sensitive latch. It's a level trigger D flip-flop. Looks like this. So D, that's Q. That's Q bar. So D flip-flop, can't believe it. Level triggered or edge triggered. Level triggered, why? So when data is here, right here, and if I give a rising edge, what's going to happen? This will be on, right? The NMOS will be on, PMOS will be off. No. It's inverted, so both of them are on. It's transmission gate, right? Whenever this is on, this will be on as well, because I inverted the clock. The rising edge here will be a falling edge, which is a voltage low for the PMOS. It's going to turn on the PMOS as well. So D will be passed to here, right? What's next? And that's it. That's why it's a not good design, because it's a level trigger. Whenever it's voltage on, voltage high during this cycle, if D changes, it's going to affect the result here. Because there's no switch. It's going to directly pass. It's just an inverter. There's no switch. It's going to pass to here. Another inverter pass to here. So we got a Q and Q not changed because of the D has been changed. So that's why it's not a good design. It's a level trigger. It's not a good design. So what's this one doing here? So when this is high, data has been, data will pass to here and here, right? What about this one? This is off, right? It's off. Why you need this to be off? Whenever it's passing data to here. No, it's not. If you do not turn it off, then it's going to compete with the data here. I mean, it only has one input to this one device, and you have two data feeding into here. It's going to compete. Since you don't know what is D, D can be 1 or 0, right? So whenever it's voltage low, what's going to happen? This will be off, so nothing can pass to here, and this will be on. And why do you need this to be on as that during this moment here? Is it able to hold it? Why? So this, yeah, so this guy, this structure, whenever you see this structure, it's a latch. Why is a latch? It's very stable. Why is that? High, low, high. Very stable. Because if you look into the inside structure of the inverter, what's in there? It's like you open up a path from VDD like a short. You short it to the voltage source, right? It's gonna be there forever. That's why it's a latch. Okay, it's like a memory. So whenever it's voltage low, it's a memory. It's gonna store whatever has been passed to here during the voltage high. Right? Okay, so we'll introduce the edge triggered version of this one on Wednesday. Right? See you on Wednesday.